Okay, let's continue with our source-free first order circuit. Okay, so this time it's about RL source-free circuit, right? Resistors and an inductor. Okay, so we're going to assume right away that our inductor has some energy stored, some initial values in it. So therefore, to know that, okay, we will say that there's a current, okay, I naught. So let's say the switch changes, at 0. Okay, there's a current I naught sort of left in the coil. Okay, in the coil. Okay, so there would be some energy stored in our inductor as a half L I naught square. Okay, so this is our initial conditions. So let's start with, I'm going to do it, I feel like showing you two ways of analyze this. Okay, let's say that I'm doing this with as if R and L are connected in parallel. Okay, like this. So we have this, well, the V are the same, right? But let's call this VL. Okay, since they're parallel, the V is the same. Oops, sorry. Right, and of course there's a current IR flowing through this and current IL flowing through an inductor. So if I do it with KCL, okay, KCL at point node A, at A, I would have, right, minus IR leaving the node A minus IL leaving the node A equal to 0. Or another way, it's IR plus IL equal to 0. I want to find IL, right? Because the current is the one that determined what is stored in the sort of energy in the inductor. So I want to see how the current through inductor changes, as we have these source-free conditions. Okay, well, so we have to change everything to IL. Well, IL is, this one is there already, so I'm leave it there. So how can I change IR into IL? Well, let's see. Well, let's work with IR. The only thing we know is Ohm's law, right? So therefore, IR is V over R, right? V over R. But this V across R is the same thing as VL. So it's VL over R. Okay, it's VL over R, right? So therefore, you have VL over R plus IL equal to 0. But still not in terms of IL. Right? So therefore, what are the relationship, the formula for the voltage VL and IL, right? The answer is VL, since VL is equal to L DIL dt. So therefore, substitute in there, it's L over R DIL dt plus IL equal to 0. So therefore, you get the differential equation DIL dt plus R over L IL equal to 0. Okay. What about if I connect it in, I'm working it like it's RL also. Okay. But now it's sort of like KVL. This is I, right? It's called IL because the current going through L also. This is L, right? This is L. This is R, right? Current go like this, so plus minus VR, right? And plus minus VL like this. Okay, as the current directions. So when I write down KVL of this IL mesh, it's VR plus VL equal to 0. Okay, VR is R times IL, right? VL is L DIL dt. So both of them put it in here. So RIL plus L DIL dt equal to 0. So therefore, DIL dt plus R over L IL equal to 0. Ta-da. Okay, so therefore you have your first order okay, differential equations, homogeneous. Okay, this on your right side is equal to 0, your equation is 0. So therefore, we're going to solve this, right, with differential equations, separable variables. So therefore, DIL dt, so same thing as what you did, for RC source free, right, separable of variable. So IL is one variable, another variable is the time t. So DIL over IL equal to R over L dt. So integrate both sides. Oh, I put on minus, forget minus. Okay, integrate both sides. Right, so from 0 to t. Okay, well, at t equal to 0, we say that IL has some values, I naught. Okay, and at any time t, it's some values we don't know yet, we want to find. Okay, so therefore this become ln IL, I naught to IL equal to minus R over LT from 0 to t. So ln IL minus ln I naught equal to minus R over LT. Okay, so ln IL equal to minus R over LT plus ln I naught with the property of the natural log. Okay, and take the exponential across the equations. So IL of t equal to, right, I naught e to the minus R over LT. So this is your general solutions for the RL source free. Okay, it's sort of like de-energized, okay, your inductor. Okay, in this case your time constant tau, time constant similar to RC, we also have for RL. Okay, in this case tau is equal to L over R, L over R second. Okay, second. So this is, if you remember it, you remember the process, you have to remember tau also. Okay, so let's look at an example. Ten ohms. Switch. Open at t equal to 0. 100 volt. Okay, find IL of t for t greater than 0. Oh, I actually forgot something, right? I forgot to do the review before this. Okay, okay, so let me do the review now for inductor. Sorry. Okay, I did it for capacitor, and I didn't do for this. Okay, let's do the review for inductor before we solve the problem. Okay, so for inductor, the formula for the current and voltage relationships, right, was if you have inductor, right, you have a current flowing through it and there's a voltage drop across L. Okay, as current changes across inductor, it will, due to Faraday's law, it will induce the voltage across the coil. So the formula is the voltage would depend on the changes in current. So the formula is V of t equal to L di by dt. Okay, so you want to find I, right? I of t, it would be 1 over L integrate, right, V of tau d tau, tau equal to t naught to t, anytime t, plus the initial values at t naught. Okay, so this is the voltage and current relation for inductor. Okay, the two rules for steady state, okay, DC or steady state rule. Oh, hold on, let me review this also, that if you have L connected in series, right, L total is equal to L1 plus L2 plus L3 plus L4. If you have in parallel, right, L total, so similar to the resistor, is 1 over L1 plus 1 over L2 plus 1 over L3 plus dot dot dot. Okay, so that's a total inductance values. Okay, and for the DC or steady state rules for L, okay, well, for the capacitor is voltage cannot change instantaneously, so it has to be opposite, right? Then it would be not opposite. Right. So in the inductor, things that cannot change instantaneous is the current. So current through L cannot change instantaneously. So therefore, IL at 0 plus is equal to IL at 0 minus. If the switch changes at t equal to 0. Okay, if switch changes at certain time t naught, it will be IL at t naught plus equal to IL at t naught minus, like this. Okay, another rules is this number 1, number 2. Essential rules are that if the current is fully energized, or if there's no changes anymore, if the current doesn't change anymore, no changes in current through L, okay, right? If there's no changes in current anymore, even the current is still flowing, like I equal to 5 amps flowing through inductor, okay, well, that means the IDT would become 0, and so V becomes 0. So therefore, what represent current flow? Current can flow, but no voltage drop across that part. It's called the short circuit. So if there's no changes in the current through through L, L behaves like a short circuit, right? Like short circuit. So I can flow, but VL equal to 0. So these are the two rules that you have to keep in mind as you're doing so-called ILRC circuits. Okay, so therefore let's go on to our problems now. So same thing, you want to know whether our inductor is energized or has keep some energy in the coil or not by finding the current that through the coil, okay, through the inductor. So at t equal to 0 minus, okay, so we draw a circuit. So 20, 10, switch was open, oh no, close, close, 100 volt, 50 ohms, inductor, okay, IL. Well, it say that, well, you know, this is DC values also, and it's been like this for a long time. We assume that the inductor is fully energized, so like full, you know, so therefore it would act like a short circuit, and you have to find IL at 0 minus. So this is your picture, okay. So right away, you know, you should be able to get this answer. So what is IL at 0 minus? Okay. Some of you may stare at the problem and, ooh, what? Okay. But then some of you may start as you have to do something. You can just stare at it. Okay. So you look at it, okay, current comes here and split into here, right? So current IL is a current passing through. So at least I know that, okay, current IL is the current that passed through the 50 ohms. Right, so IL is equal to current passed through 50 ohms. Okay. Well, the formula for current going through an inductor, well, and I know that, well, it means that these are in parallel, right? They're connected in parallel. I mean, this it's like the voltage source 100 volt. We have 50 ohms here. This is IL, and we have like 10 and 20 like this, right? 10 and 20. So there's 100 and this are in parallel like this, right? So you can see that, oh, okay, IL must be V equal to IR. So IL is, this is I. Oh, what am I doing? Hold on. So this I across 50. Okay. So it's V drop across 50. So it has to be V drop across 50 over 50 ohms. So what is the V drop across 50 right here? Okay. V drops across 50. So it's this point is the same thing, this point is the same thing, then parallel. So therefore V is equal to 100 volt over 50. So equal to 2 amps. Oops. 2 amps. Okay. Then finish. So we go to, oh, okay, there's some initial values, some energy stored in it. It's 2 amps. So then go on, switch changes at t equal to 0 plus. Switch opens, right? So this open up. Right, so this inductor, 50 ohms, 10 ohms, 20 ohms, and this is IL at 0 plus equal to IL at 0 minus equal to 2 amps. So 2 amps flowing. Okay, how does it flow? Let's see, is there a source connected to it? Flow, well, this is open, so therefore the voltage source gone. So now you have RL source free. RL source free. Okay. But there are 3 R's altogether. So similar to the RC, right? The R equivalent in RC source free. Okay. Your tau in this case, right? Your tau in this case, well, we want to, it's RL source free already. So you know that IL of t would be equal to I naught e to the minus R over LT, right? Okay. So therefore, what's R? But there's more than one R. So R become R equivalent. Okay, so R equivalent. So what is R then? Well, R similar to the RC. It's a total resistance. Okay, looking from the inductor point of view. So therefore, this is nothing but everything connected in series. So 50 plus 10 plus 20 equal to 80 ohms. So therefore, IL of t is equal to 2, right? Because this is 2. I naught is 2. E to the minus 80 over 0.2 t amps. So the answer is IL of t is 2 e to the minus 400 t amps. Okay, so similar concept. Okay, one last example. One last example I'm going to do. So 9 amp, 6 ohms. This is an interesting problem. Find V of t for t greater than 0. The switch, okay, changes from A to B at t equal to 0. This is the condition. Sorry. It has been a cool weather this past week, right? Starting like about 18 degrees on Monday. But today is Friday already, and it's cool, it's still cool, but it's not as cool as on Monday. It's a wonderful time. It's like real winter arrived in Thailand now. Okay, so even though you realize that, hey, the question asked for the voltage drop across the 6 ohm, nothing to do with, L at all, the inductor. But, as I told you, when you have a problem involving energy storage, okay, involving switch in a problem, some changes in a problem, you have to find out is there anything stored in that energy storage or not. If it's a capacitor, you have to find VC, right? If it's an inductor, you find IL. Okay, depending on which direction your IL you want. Okay, so anyway, I'm going to have to look at t equal to 0 minus. Okay, so 9 amp, 6 ohms, switch still at point A, so 3 ohms, inductor 72. The problem has been like this for a long time until t equal to 0 minus. 9 amp has been feeding the circuit for a long time, DC values, so there's no current changes in the inductor anymore. It would flow like this, like this, sort of like at the beginning like this, but then as time goes by, right, so-called inductor, there's the constant values of current going through inductor, so inductor behaves like a short circuit. So now, if at t equal to 0 minus, your circuit turns out to be like this. So 9 amps goes here, goes up here, right? Let's call it I1, goes here, it's called IL. Of course, it doesn't go here anymore, right? So IL goes here and goes like this. It doesn't go here anymore because it's shorted 72 ohms out. So therefore, find IL at 0 minus. We want to check that. So current 9 amps come to this point divided into I1 and IL. The 9 amp divide itself into two portions, 6 ohms and, passing through the 3 ohms. So therefore, using current dividers, IL 0 minus would be, and it divided into only two portions, right? Only two paths. I'm using my short circuit formula for the current divider into two paths. So IL 0 minus become 6 over 6 plus 3 times 9 amps, so equal to 6 amps. Okay, so that's that, right? Then at t equal to 0 plus, hold on, the switch changed place, right? Hold on, right? So it becomes, let me look at the picture again. Okay, the switch changed to B. Switch changed to B. So therefore, you're left with 6 ohms plus minus V, right? And this is the 3 ohms, inductor, and 72 ohms. This become your circuit, right? And this is IL at 0 plus. Well, IL at 0 plus, right, doesn't change instantaneously, so equal to IL 0 at 0 minus equal to 6 amps. So we have 6 amps flowing through here. So right now it's become RL source free again, right? So therefore, my IL would, sort of like now become like almost like a current source supplying this circuit. So what's IL looks like, okay, as times go to t equal to 0. Okay, so IL of t would be in term of I naught, right? E to minus t over tau, okay, minus t over tau. So therefore, can you find it out, right? What tau is? Okay. So let's see, R over L. So your L is a half, right? Your R equivalent is equal to, well, you have to look, 6, 3, right? Your L is here, and this is 72 ohms. So R total equal to R equivalent here. So R total is equal to, goes up here. Imagine there's a current flow here. We go through 3 and 6. So 3 and 6 is in series, right? And then it's parallel with 72. So 6 plus 3 parallel with 72 equal to 8 ohms. Okay, so can you find your tau? So tau is L over R. So tau is equal to L over R equivalent. L is a half, right, over 8, right? So therefore, 1 over 16, okay, second, right? So therefore, your IL of t becomes I naught is 6 e to the minus t over 1 over 16, okay, amps. So therefore, IL of t is equal to 6 e to the minus 16 t amperes. But that's IL, correct? That's IL. We want to find V, which is across 6 ohms right here. So we have to look. Well, we know IL. So what happened to our IL? So now IL goes up here, right? And then it divides itself into 2 paths, right? So let's call this IX, okay, into 2 paths. Right? If I can find Ix, right? Ix pass through 6 ohms. 6 times Ix is V. So I have to find Ix. Okay, so let me draw this here. So let's say this is, so I'm drawing this. 6 and 3, 6 ohm. We have to find V, right? Across 6 ohms. Not nice. Oh my. One more time. So it becomes 3 ohms. This is 6 ohm. Right, inductor, and this is 72 ohms, right? This is IL of t. So go Ix like this, right, and split into 2 paths, right? One into 6 and 3, right, and one into 72. So using current dividers, so Ix of t would be equal to 72 over the sum of 72 and 6 and 3 multiplied by IL of t, right? So therefore, it would become, you use your calculator, please. So your Ix, so Ix of t become 72 over 72 plus 9 times IL, which is 6 e to the minus 16 t amps. So Ix of t is 16 over 3 e to the minus 16 t amps. So therefore, V of t is equal to 6 Ix. So it's turn out to be 6 times 16 over 3 e to the minus 16 t volt. So therefore, V of t, therefore, V of t equal to 3 and 2, sorry, I'm being Thai. Okay, so 32 e to the minus 16 t volt. Finish. So that's your answer. All right. Go back, take your time to so-called absorb, okay, and analyze this slowly on your own. Now take a piece of paper, blank paper, write down the problems, okay, and try to solve it by yourself, okay. Try not to look at the solutions. You know what I did, okay. All right, so that's wrap up the RL source free. Okay, thank you. See you later.